Physics students, welcome to the third and final video for topic 5.4, magnetism, magnetic effects of electric currents. And in this video, I'm going to talk about current carrying conductors and magnetic fields. All that really means is we're going to talk about how current carrying wires or wires with electric current going through them behave in magnetic fields. Now you know that the magnetic force on a moving charge is given by QVB sine theta, QV cross B, okay? Now it's a very simple extension to the idea of current through a wire in magnetic field, because of course current is just a whole bunch of charge moving per unit time, right? So instead of talking about one charge moving through a B field, we will now talk about many of them, okay? Now, in this particular case, a very simple example here, I have a uniform B field between the north and south pole pointing downwards in this diagram. I connect this wire here, which is sort of in the shape of a square, okay? And I've got it connected to a battery, and there's a current that flows through this wire, okay? Now, because of the right-hand rule, all right, which is shown here, with the B field downwards and the current in the same direction as the velocity, because of course that's what it is, you see that the force in this case acts to move the wire from this position up to this position, okay? Now, one thing you note here with the right-hand rule is that this is assuming that the current is positive moving charge, and so that's called conventional current, as you know from our previous studies of circuits, okay? The reality is that it's not the positive current that flows, it's the negative current that flows, okay? But anyway, this is how we do it with the right-hand rule, okay? So the wire itself experiences a force and moves, okay? Note the direction of I, which is in the same as that's the direction of the velocity. Remember QVB sine theta for each charge. The magnetic force exerted on the length L of the wire is the net force acting on the total charge moving in the wire, okay? And I have to point out that actually it's this part of the wire that has a force acting on it, not the part that's parallel to the B field, of course, because of that cross product between V and B. If in the time delta t, delta q travels through the wire, then the total force is obviously delta q times VB sine theta, okay? Now, using that equation again, if we multiply the right-hand side of this equation by delta t over delta t, which is just another way of saying the number 1, we can extract something really interesting and useful here, okay? Note that I can bring out the q and say I have a delta q over delta t right here. The other delta t on the top, I can lump with the v delta t. Notice that delta q over delta t is the current, and v delta t is just the distance over which that charge moves, which of course is the length of the wire. And I end up with the following equation, which is in your data booklet. F equals BIL sine theta or ILB sine theta. In this case, theta is still the direction between the velocity vector and the B field vector, but more specifically and more easily imaginable is that it's the angle between the straight wire and the B field, okay? So it's pretty simple. It's a pretty simple extension. Really, this equation is saying the same thing as F equals QVB. It's just stated in a different way, right? Okay. Now, let's try a couple of examples. Okay, what is the force experienced by a 30 centimeter long straight wire carrying a 2 amp current placed in a perpendicular magnetic flux field of flux density 6 micro Tesla, okay? Don't worry about this term flux density. That just means that the magnetic field is 6 micro Tesla, okay? Now, I have to show you that tell you that this diagram right here is a little bit misleading. It shows that the wire and the field are at angles, but it's really meant to be 3D, where the current and the field are actually at right angles, and that's that right angle right there. So you're kind of seeing it from a, I guess from a kind of an upwards point of view from an angle. So go ahead and try this one. Very simple. Everything's orthogonal. Okay. All right. So this is just a case of F equals BIL, which is 3.6 times 10 to the minus 6 newtons. So that wire actually moves upwards in that field. Okay. Okay. A straight wire of length 0.5 meters carries a current of 2 amps in a north-south direction. If the wire is placed in a magnetic field of 20 microtesla directed into the page, what is the force on the wire? Again, okay, very straightforward, okay. Better to draw a picture of this, north-south being up and down. It's actually kind of a funny way to describe that problem. And I get 0.02 newtons to the left as shown, okay. So again, V, B, okay, good, right? Okay. Okay. Now remember the B field patterns of moving charges. Okay. We had this sort of the very earliest incarnation of what we call the right-hand rule, where the thumb is in the direction of the current, and we had the B field going around. I'm going to quantify that for you now. Okay. It turns out that you see how in this diagram how the field lines are closer together the closer you are to the wire, and they get farther apart the farther you are away. That means, or that suggests, that B is inversely proportional to the radius or the distance from the wire. And in fact, that is the case. If you graph B against R, you get a 1 or an inverse relationship. Obviously, from this equation, B is proportional to I, so B graphed against I would be a straight line, okay? There's a new variable here that you need to be aware of, and that's called mu naught. And don't worry, the 2 pi obviously comes from the fact, you won't have to derive this, 2 pi comes from the fact that the field itself is radial or circular, okay? Mu naught is called the magnetic permeability in a vacuum. Don't worry about that necessarily. It's kind of a funky constant, and it's equal to 4 pi times 10 to the minus 7 newtons per ampere squared. Now, the reality, and I'll do a couple of problems like this, when you're problem solving, notice that you have then a 4 pi over a 2 pi, which ends up being a 2 on top. So you have a 2i times 10 to the minus 7 over r. Okay, and that's an easier way to think about that particular equation. Now, in a solenoid, you should be familiar with the following equation, and that is that the B field inside is equal to mu naught times n, which is the number of turns of the wire times the current over the length. And it's not the length of the wire, but it's the length of all the coils together. That's important for you guys to realize that, okay? So again, B equals mu naught I over 2 pi r, and B equals mu naught Ni over L. Neither of these are in your data booklet, but you should be familiar with them, okay? All right. Okay, so let's take a look. This problem solving can get a little bit complicated. Okay, let's try example 7. You might want to pause this video and try it on your own. And remember, I've given you that I've made accessible to you the handout that has this example in the paper. So go ahead and try it on your own first. Okay. All right. So it's asking the magnitude and direction of the B field at point P. Now, at point P, there are actually 2 magnetic fields that we need to add up to get the total B field. There's a field as a result of the 2 amp wire going to the right, and there's a field from the 2 amp wire going to the left. Okay, now, which of these wires would have the greater effect? Which of these wires would have the greater effect at point P? Or which of the fields would be felt most strongly at point P? Clearly, it's the bottom wire because it's closer, right? Remember, the B is proportional to 1 over R, okay? So what you need to do is you need to use your right hand with your thumb placed in the direction of the current, okay? And you need to think about, as a result of the bottom wire, the B field is coming out directly towards you, right? As a result of the top wire, the B field is going in. But that field is weaker than the field coming out as a result of the bottom wire. Therefore, the net field should be coming out of the page towards you. Okay? All right, so what I'm going to do is I'm just going to figure out what both of them are. Okay? The top wire I'm calling B sub t. That is 2 times 10 to the minus 6 Tesla. Okay? Inwards, of course. And the bottom is 4 times 10 to the minus 6 outwards, which of course, like I said, was greater. So therefore, the net field is the addition of the 2, where notice that one of them would be negative, and it doesn't matter to me. I guess it makes sense to think about the B field coming out as the positive and the one going in as the negative. In that case, it would be negative here, and this should be a negative. And then you get 2 times 10 to the minus 6 Tesla out. Pretty cool, huh? Okay. All right, so obviously 2 parallel wires exert forces on one another, okay? All right, so if you have parallel currents, and you can test this again, putting your thumb in the direction of the current, all right? Parallel currents, and actually that's not necessarily the way to use that. You would actually use the right-hand rule for that, okay? Using the right-hand rule where I is in the direction of the current, notice that 2 parallel currents or currents in the same direction would have those wires would actually be attracted to each other. Parallel currents, forces pulling together, okay? And you'd have a magnetic field that looks like this between 2 parallel wires with with currents in the same direction. If they're in the opposite direction or anti-parallel, you have them opposing one another. And in this case, the magnetic field would look like this. This is an important slide. The bottom half of the slide is very important for you to understand how to visualize these two types of fields. You will be asked questions like this on the IB with two wires for sure. Okay? Okay. And in fact, this law is called Ampere's force law. Okay? If the currents are in the same direction, the wires attract one another. If they're in the opposite directions, the wires repel one another. And again, you can use your right-hand rule to figure this out, right? Okay? So once again, in the vicinity of wire 1 is affected by the B field from wire 2. Wire 2 is affected by the B field from wire 1, okay? So you have two sets of moving charges, in other words, a current-carrying wire in a B field. But the B fields that affect them are the B fields created by the other wire. Okay, so again, Ampere's force law. If the currents are in the same direction, the wires attract. If the currents are in opposite directions, the wires repel. And in fact, what's really interesting about this is that this particular force is actually used to define the ampere. Remember, the ampere is kind of one of those oddball SI base units. It kind of seems like doesn't really seem to fit in as one of the basic the 6 SI base units. A standard definition of the ampere is as follows. It is the constant current that will produce, in other words, 1 amp. It's the constant current that will produce an attractive force of exactly 2 times 10 to the minus 7 newtons per meter between two straight parallel wires of infinite length and negligible cross-sectional area placed 1 meter apart in a vacuum. If that's not one of the weirdest definitions of a unit, in physics. I mean, it's kind of interesting, but that is the actual scientific definition of the ampere. This may come up in an IB question in terms of using parallel or using long parallel wires with currents in them to define the ampere. I've seen that question before. Okay? All right. Okay, last example. Example 8. The drawing shows two parallel straight wires that are very long. They're infinitely long. For your purposes, the wires are separated by a distance of 0.065 meters and carry currents of 15 and 7 amps. Find the magnitude and direction of the force that the magnetic field of wire 1 applies to a 1.5 meter section of wire 2 when the currents travel in opposite directions and in the same direction. Good luck on this. Pause the video and use the worksheet I gave you with ample space to solve this problem before you see my solution. Okay, well, of course, when they're traveling in opposite directions, there's a repulsion. When they're traveling in the same direction, there's an attraction, okay? So if we consider a length of wire 2 called L and make that 1.5 meters, okay? All right, the magnetic force on this wire, on wire 1 on this length L would be, I'm denoting F12 equals BI12 times L, okay? And this is the magnetic field from wire 1 on wire 2 in this equation right here. And that's equal to mu naught I1 over 2 pi r, where r is the distance between the wires, of course, okay? So, therefore, F12 equals mu naught I1 I2L over 2 pi r. Put the numbers in and you get 4 times 10 to the minus 4 newtons, okay? If they're in the opposite directions, they're repulsive. If they're in the same direction, they're attractive, okay? So this is a beautiful, really beautiful problem in the sense that it's combining two of our basic equations, F equals BIL and B equals mu naught I over 2 pi r, okay?